Okay, we're going to do inclines. Newton's second law, incline edition. We're allowed to what? So, I don't know. I can't say that. Yeah, I can't say that. So, inclines. You do you. Inclines. So, if I were looking at a box and this box has a mass, what would be the forces acting on said box? Okay. So we have a normal force going up and we have a gravity force pulling down. They are roughly the same, right? So we've got Fg or mg and we've got a normal force pulling up this way, right? If it is, like for example, if the normal force isn't able to push up, then the gravity will make it sink down. Quicksand is one of those things. So like you try to step on it and the normal force literally can't push back up, so you end up sinking anyway. So now we're going to make our lives a little bit more interesting though, because we were on flat surfaces. Now we're going to be on a ramp. And ramps occur in real life really frequently. So I'm going to go ahead and I'm going to put our box, but our box is going to be on the ramp. Okay. Now, what forces do we have acting on this? Well, there is no like what do you mean that way force? It's just sitting there right now. Let's assume there's no friction. Let's assume there's no friction inside there either. So no friction. If there's no friction, that's not true. That's not true. Yeah, because if you said if there's no friction, it's not moving. That's not true because are forces. There are forces acting on this though. Okay. So gravity. Okay, what way is gravity pointing? Down. 90 degrees to the box like this. Like this. Okay, so like right, right, but this isn't down. That's not kind of down doesn't count. You can't do kind of down. That doesn't count. All right. No, these ideas are scary. I'm not sure what's going on here. These ideas are scary. What's going on? Yes, it is. Okay, now erase that because the digital students can't actually see that. There we go. Okay, so there is a normal force that is 90 degrees to the surface, and there is a force of gravity, and the force of gravity is mg, and it always, no matter what, points straight down. Okay, so here's because you're on Earth, right? And if you're on Earth, the force of gravity has to be pointing straight down. So right now, then if you're on Mars, then the force of gravity will be pointing downwards towards the planet. Okay. So it does make a difference because the force of gravity is it doesn't always necessarily like I say down, but like if you're on the like in Europe versus Australia, then obviously if you were to ask this person, if you were to ask this person which way is gravity pointing, they'd say down. And then if you ask this person down here which way is gravity pointing, they'd say down. Okay, but no, they wouldn't. They would say down. They would literally say down. Okay, because your forces are relative. Okay, and the same thing is happening here. When you're on the ramp, gravity is still pointing downwards. Okay, but we're on the ramp, so the normal force is going to be pointing 90 degrees to it as well. So we have to keep in mind, no matter what, the force of gravity is pointing straight down. That is the first big thing and the first big hiccup that a lot of people forget whenever they see like forces on inclines. The force of gravity always points straight down, no matter what. Okay. Well, I know I did. You're right. You're right. I do try to make y'all double check yourselves, but that's okay. There's nothing wrong with a little double checking. Here's a double check. What is the line of action? Like this? Oh, 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 parallel to the ramp. Okay. Oh no, I erased my arrow. Oh crap, that's even worse. Oh well, I'm gonna leave it. So like this? Okay, that makes sense because if it's gonna move down the ramp, it's gonna move down like this way. So if we were to look at the box at a different point in time, it would be along this line of action. And that makes a lot of sense to me. Okay. It is, and we'll get into that later. Yeah, it is. That's true. That's a work problem, and that's for later. So the first thing that we're going to need to do whenever we start analyzing this problem is that we're going to break up the forces. Okay, we're going to break up the forces along the line of action. Break up the forces along the line of action. And what that means is that we're going to be breaking this into components. Okay, so what I'm going to do is I'm going to use a green arrow and I'm going to break apart my mg into a quote unquote horizontal component and then a quote unquote vertical component. The green is going to be the vertical one and the red one is going to be the horizontal one. Okay. Now, the reason why I broke it apart in this fashion is that the red arrow, the component of gravity that is going with the line of action, is the component that's going to be accelerating the object down the ramp. Because if you have like, say you take a can of soup or something and you just like lay it on the rolly side and you let it go down the ramp, it's going to go. Like, you don't just put it on there and then like expect it to stand still. There's not a lot of friction if you include the rolling side, so it will just roll down the ramp and it will accelerate. And it will accelerate according to this red arrow. Okay. Oh no. There's a dot there now. There we go. Okay, so it's going to accelerate according to that arrow. Now, there is a little bit of good news, and the good news is that if you know the angle of the incline, which I'm going to write as the Greek letter theta, if you know the angle of the incline, that is the same angle as the angle from which your gravity and your vertical component are. So if this is because of geometry and similar triangles, basically you can set up, I'm going to try it this way. The right angle for the ramp is right here, and the right angle for this ramp is right here. So you can take it and flip it over and make it bigger, and you essentially have the same triangle in terms of angles. So you have a similar triangle. Okay, and yeah, we are going to use sine, cosine, and tangent now. So I'm going to I'm going to make this bigger. So I'm going to go make a really big mg like this, and then I'm going to make my components go down like this. Okay. If this is the angle, which is the angle theta, it's yep, 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 that's true. Yeah. And okay, so this force down here, this is going to be the Newton's third law to the normal force, because we know one of two things. Okay, the normal force is not going to be greater than this downward force of gravity because the box isn't floating in the air, and we also know that the force of gravity is not going to be greater than the normal force because it's not punching through the ramp. Okay, if the force of gravity was greater than the normal force, it would literally sink down the ramp, and we don't want it to do that. So they're going to be equal to each other. So this component right here is going to be equal to the normal force. So I'm going to write here normal. Okay, and this force down here is going to be the accelerating force. If I can spell accelerating right, that's a big thing. Accelerating. All right, now we can get expressions for these. We know that the hypotenuse of the right triangle is mg. So if I want to find out what this adjacent side is, we can use SOHCAHTOA to find out what it is. Okay, so if it's the adjacent side, do we want to use the sine, the cosine, or tangent? It's the CA part, right? So it's the CAH. So we're going to do that. Okay, the cosine of the angle is equal to the adjacent over the hypotenuse, but instead of writing hypotenuse, I'm just going to put in mg because we already know that that's gravity. We already know that that's mass times 9.8 meters per second. It's pretty easy to find the mass, and it's pretty easy to know that we're on Earth. So those two numbers should be known. Okay? So if we need to solve for that component, I'm just going to multiply both sides by a. So my normal force is going to be, go ahead. Did I just say multiply by a? I'm sorry. I'm going to multiply both sides. Yeah, you're right. You're right. You're right. I'm going to multiply both sides by mg. Okay. And these are going to cancel. Bye-bye. So that leaves me with my adjacent side, or my normal force, is going to be equal to mg cosine theta. Yeah, no g. Cosine theta. Okay. So the normal force is mg cosine theta. The accelerating force is going to be using the opposite side. That A stands for the adjacent side. So why don't I call it, yeah, why don't I call it ADJ instead for adjacent? Yeah, little a normally stands for acceleration, or little g for Earth acceleration. So capital A, I'm just referring to the adjacent side, the force of the adjacent side. Okay. So what you're normally going to see from here on out, because I'm not going to write ADJ equals mg cosine theta, normally you're going to see that the normal force is equal to mg cosine theta, and that's for a ramp. Okay. Anytime you're dealing with the normal force on a ramp, then the force for the normal pushing back up against it is going to be mg cosine theta. And somewhere in this screen, I can probably squeeze in the sine. I'm going to erase my little Australian people. There we go. They're gone. And this downward part, this one depends on the so part. So it's the sine of the angle is going to be equal to the opposite side over the hypotenuse. So the opposite side, I'm going to write OPP. And then for the bottom part, I'm going to write, what is that, mg? That's the hypotenuse, right? So mg. If I'm wanting to solve for the opposite side, then the opposite side, I'm going to multiply both sides by mg again. So that's going to become mg sine theta. Mg sine theta. So this bottom part is equal to mg sine theta. Okay? And yeah, if there is a little bit of black magic that's involved here, and we can play around with this stuff if we want to, but I think we'll probably just leave it that way right now. So the good news, because I know y'all are right. You said this is analytical, and this is something that you don't have to, that you don't necessarily like. But the good news is that with mg sine theta and mg cosine theta, if you solve it analytically like this situation for an incline never changes. So you're like, hey, what's the force of the thing moving down the ramp? Mg sine theta. That's it. Okay, so if you know mg, if you know the mass, if you know gravity, and you know the angle, then you're good to go. Okay. If you're looking for the normal force, it's mg cosine theta. If you know the mass, if you know gravity, and you know the cosine of theta, you have it. Basically, the analytical solution allows you to derive formulas, and it allows you to make expressions that you can use to solve every single time. You don't have to go back and do the problem every time. When I did physics in high school, my physics teacher would not do um, the derivation of the formula immediately. They would make me go through the algebra first, and then after they made us go through the algebra, then they would be like, oh yeah, by the way, you can do this. And I was like, oh, okay, that actually makes a lot of sense. Okay. So There you have it. Um, they did tell it to me eventually, but I didn't have AP Physics, so all right. Regular old physics. It's still good though. I still learn most of this stuff. It wasn't really that much different. So that is true. Okay. So let us try one. So if we just make an incline, and this one will be a little bit nicer for you guys because we can do a little bit of plug and chug. Let's say that the angle is 25 degrees, and let's say that the box up above has a mass of 5 kilograms. And let's say that the distance from here to the end of the ramp is, I don't know, why don't we go with 2.5 meters? We might, depending on what I'm going to ask you for. So like it will, because I could ask you how long does it take to go down to the bottom of the ramp. So for our acceleration, it might not make a big difference. But if I ask more to the question, then yeah, we might need it. In terms of forces, though, no, we do not need the actual distance or length of the ramp. But I think with this 5 kilograms and 25 degrees, I think we can find the acceleration of it down the ramp if we're ignoring friction. So I think we're going to do that. Let's ignore friction and let's say, what is the acceleration going down the ramp? Okay, so what is the acceleration going down the ramp? So how would we set this up? That's kind of what we have right now, right? You know, people drilling through the walls. Okay, so we have two forces, right? So we have gravity going down this way, and we have a normal force pulling up. So let's identify what these forces are, and then we'll break them up into their components. My line of action, down the ramp, like this. Okay, what is the force of gravity? Okay, so we've got forces. We can use 10, totally can. So F of G has a, I don't know, what is the force of gravity? It's not 10. It's not 10. It's definitely not 10. The force of gravity is not 10. 50, yeah. Mass times acceleration, right? Yeah, 50. So the force of gravity is 50 newtons. Okay, and we can use it as a negative if we want to, but we can also just have the understanding that this is going to be going down the ramp and that we assume that our acceleration is going to be negative. It doesn't matter to me which way y'all do this. Which would y'all prefer? It's going down, so it should be negative. Let's do it that way then. So I'm going to put a negative here. F of G, negative 50 newtons. Okay. Right. So like yeah, there's definitely several different ways to think about it. So we're gonna say that if it's going down, it's gonna be in the negative direction. So we're gonna go with that. Okay. Now we also have the poor English teachers across the hallway. They're not gonna be enjoying this part. That's for sure. For those of you for digital students, there's construction going on, so I don't think y'all can hear it, but there's a lot of destruction derby. I think they are going to knock that window out up at the top. Yeah, I think it's going to be a hallway on top and bottom, if I remember correctly. But don't quote me on that because I don't know for sure. Plans change and all that good stuff. All right, we also know the normal force, but we don't know exactly what it is yet. So I'm just going to put a question mark. Okay. Now we do know that we're going to break this apart. So if we look at the line of action, there's going to be a normal force and there's going to be an accelerating force. So I'm going to call that FA for the accelerating force. Okay. Now these are both going to be based off of the force of gravity. So what I'm going to do is I'm basically just going to put like a little bracket by this F of G because both of these are going to be related. So we've got negative 50 newtons, and that negative 50 newtons is going to be related to the normal force, and that negative 50 newtons is going to be related to the applied force as well. Okay, so how do we get the normal force? Which one? Y cosine. Which one? It's cosine? Okay, where's our angle? Our angle is 25 degrees, right? So that means that the one that we're referencing up here is this one. So the normal force is the adjacent side. So that's the cosine, okay? And then the opposite side is going to be the applied force. So that's the sine, okay? So the normal force is going to be equal to, oh, poor computer, it's not, mg cosine theta. Okay, do we have all those numbers? Okay, tell me what it is then. Make sure your calculator is in degree mode. Degree mode, degree mode, degree mode. All the time. 45.31 second. I need a second. That's okay, some of us are still writing stuff down. 45.32. We're okay? How about just 45.3? Is that okay? All right, so we're going to put 45.3 newtons for that one. Positive or negative? 43.5 newtons. For the normal force? Okay, so like we're looking at this component down here, right? So this component from gravity is negative, but that corresponds to the normal force, which is now positive. There we go. Okay, so we've got a negative in, and then we've got it flipped. This is going to be a positive 43.5 newtons. Okay, what about the FA? The FA, the applied force. Break it down for me first. FA, mg sine theta. Okay, we have theta, we have m, we have g. Okay, 21.1, 21.1. Okay, good. So then 21.1 newtons. Okay, 21.1 newtons. Oops, I can't even write my n right. There we go. 21.1 newtons. Okay, now if you do the Pythagorean theorem, if you do 43.5 squared plus 21.1 squared, you're going to get 50. Okay, because if you take those two components, or you're going to get something really close to 50. Like I've had people before be like, no, I got 49.999. It's like, come on, it's like 50. It's pretty close to there. 45.3? Oh, did I dyslexia that? I'm sorry. You're right. You're totally right. 45.3. I totally did dyslexia that. 45.3. There we go. All right, now my statement still stands. If you take these two, yeah, if you take these two numbers and you do the Pythagorean theorem to them, you should get 50, and that's a good way to double check and make sure that you actually did it correctly. You'll get 50 squared, yeah. Okay, so like if you solve it as if you're trying to find the hypotenuse will be 50. Okay, 49.9, close enough. Yeah, very good. Okay. So there's our two forces. Can we find the acceleration from these forces? Yes. So I'm going to go ahead and I'm going to write down, I know my normal force is 45.3 newtons. Okay, so how do I find the acceleration? Okay, we're going to do F equals ma. So I'm going to go ahead and I'm going to write mass of the system times the acceleration. Fortunately, our system only has one thing here. There's just one box, right? So we don't have to worry about, I always write mass of the system because that helps me remember that sometimes I have to calculate multiple masses, but there's only one box here, so we're okay. What is the mass of our system? It's only because I've made a ton of mistakes before. So 5 kilograms, okay, and then times the acceleration. And the FA is what we're going to be using, the accelerating force. So 21.1. All right, so the acceleration is going to end up being 21.1 newtons divided by 5 kilograms. 4.22. Second? Seems reasonable. 4.22 meters per second squared. 4.22. Good. Okay, so we found our acceleration, and that if that was the only question, then that would be it. That's all that we would need. That's never how that works in AP Physics, right? In AP Physics, they always want to try to ask something else. So the next thing that they could ask you is they could ask you, how long will it take to go down the ramp? How long will it take to go down the ramp? There we go. Okay, so we have our acceleration, and if we're looking for how long will it take, this object is going to be accelerating down the ramp at a uniform rate, which means we're going to need to do what? Find the what? Speed? Okay, so we can find out how fast it's moving. We can do that. Do we have enough information? I want us to find the time. How long does it take us to go down the ramp? We can find the speed too. Do we need to know the length? The 2.5 meters is the length of the ramp. So I think we need a little I think we need a little DVAT here. I think it's DVAT time. I, I don't think we can small brain this. I don't think so. DVAT. We have 5 pieces of information here for our DVAT. Do we have the distance? Yeah, 2.5 meters. Do we have the VI? Vernon? Do we have the DI? Do we have the VI? Sorry. Do we have the VI? 0? Okay. 0 meters per second. Okay. Good. VF? Question mark, right? Do we know the acceleration? 4.22 meters per second squared. Do we know the time? No. Okay, so we're going to have to find out some way to be able to get this. No, the acceleration is for. Okay, go one more time. Lay it on me one more time. Are you sure? I don't think that's how that works. I don't think that's how that works. I think you're going to hit 4.22 meters after 1 second because you're not traveling at a constant speed of 4.22 meters per second. You're speeding up. So you have to start at 0 and then you're making it to 4.22 meters per second. So after 1 second, you will be going at 4.22 meters per second, but you will not have been traveling 4.22 meters. Okay, so the linear relationship between acceleration is between acceleration and velocity, not acceleration and displacement, which means you cannot small brain this. We have to do the kinematic equations. An eighth of a second. 2.5 meters in an eighth of a second. Oh, 0.8 seconds. Okay, an eighth of a second is not zero point 0.8 seconds. Okay, just making sure that we're clear on that. What kinematic equation are we going to use? We have options. Yeah, we don't have VF, so we can't use VF. Displacement equals VIT plus 1/2 AT squared. I'm going to have to use A instead of G this time. We know that the VI is 0, so this goes away. So my displacement is equal to 1/2 4.22 for the acceleration times time squared, and my distance is 2.5. Yeah, I could have. I just okay. So yeah, half of 4.22 is 2.11. So 2.5 equals 2.11 t squared. Your t squared is going to be, divide both sides by 2.11. It's going to be 2.5 divided by 2.11. So t squared is equal to 1.18. Do we take a square root? Time is equal to 1.09 seconds. So it's going to take a little bit longer than you guys thought. You had a good estimate, but it's going to take a little bit longer than that. So our total time to travel down the ramp is going to be 1.09 seconds. 1.09 seconds. Ah. Do we want to add friction? Friction friction is a thing. I haven't really talked about friction yet though. So, yes, we do. Let's just do it. Okay. I'm gonna give you a little talk about friction. Okay, I'm gonna give you a little talk about friction. So, well, wait a minute though, because like, yeah, it'll take more time, not less time, because friction's gonna slow it down, not speed it up. Okay, so like, you only want to deal with friction because you want to be right. Is that how this works? I don't actually, I don't know, I don't know. Friction, kind of works like that. Like what causes friction to start with? Yeah, so like on a microscopic level, there are like if you look at something under a microscope, it's not perfectly smooth. There's like a bunch of jagged edges on it. The more jagged it is, the more friction you're going to have on the objects themselves. So friction in general is just like a resistance to motion. So what actually causes that resistance to motion is all those little jagged edges. Now, we can't measure all those jagged edges. So we have to come up with like a way to describe it without actually saying like, well, how many jagged edges are you going to have per centimeter squared of on an object? That would just like that'd be crazy. We don't want to really talk about all of that stuff. So what we're going to do instead is we're going to create something called a coefficient of friction. So this symbol that looks like a U with a little tail, yes, it is the Greek letter mu. Okay, so it is called the coefficient of friction, and we're going to be using this a lot. And the reason why I have to say it now is because it depends on the actual material that the ramp has on it. Like if it was a carpeted ramp, it would have a really high coefficient of friction. Because or if it was ice, yeah, if it was ice, it would have a really low coefficient of friction. You would try to walk down the ramp and you would just slide down it instead of like actually sticking to it. Okay? Skateboards have a so that's you actually skateboards have a really high coefficient of friction. Okay, asphalt to pavement has a really high, and car tires have a really high coefficient of friction. Because think about it, you want the car to roll. You want the tire. No, sorry, you don't want the car to roll. You want the tire to roll. You do not want the tire to slide. Okay, because when the tire slides, you have no control. When the tire rolls, you have control because you can stop it when you want to. If the tire slides, you don't have control. You try to turn on the brakes and you just keep going. Okay? So, car tires and asphalt and skateboards and stuff like that, they actually have really high coefficients of friction because you are moving, but you are moving in a rolly fashion. Okay? So, but that rolly is always still stuck to the ground and you want it to stay stuck to the ground. Okay? Coefficients of friction go usually between numbers from 0 to 1. Okay? So if you have a coefficient of friction of 0, then you have a frictionless surface. If you have something that has a coefficient, I'm trying to get rid of that. There we go. If you have something that has a coefficient of 1, then that's going to be a really high friction environment. Can you get a coefficient of friction greater than 1? Yes, absolutely. Okay? So if we do labs and we find the coefficient of friction and it comes out to be like 4 or 5, depending on the materials that we're using, yeah, that can actually happen. So we're going to be seeing this coefficient of friction come up a lot. Okay? The way that we calculate friction is going to be depending on the situation, But in a large majority of the cases in AP Physics, if you have an object that is being pushed, so let's say that there's an applied force going this direction, there's going to be a opposite acting force of friction that's usually less than the applied force. So you're still going forward, but there's something that's pulling you back. Okay, the force of friction is going to be equal to the um, coefficient of friction times the normal force. Or in other words, friction is fun. So you have friction is equal to the coefficient of friction times the normal force. F mu n. I can't say FU n, it's F mu n. Okay? So F mu n. So if we know the coefficient of friction and we know the normal force, then we can calculate what the friction is. If we don't have the coefficient of friction, they're going to have to give us some way that we can calculate the frictional force in order to be able to solve the problem without going insane in the process. Okay? Because when we're dealing with friction, the coefficient of friction is how we deal with like the microscopic differences between those surfaces, because you really don't want to take a microscope and start counting all those ridges. We would never get anything done. So instead, we just make a number for it, a coefficient of friction. Okay? So if we added friction to this, let's give it a realistic coefficient of friction. Let's say that on a regular surface, let's say that the coefficient of friction is like 0.3. 0.7 is pretty high friction. So if we go back to our incline, oh god, I don't even have any like room up here. Like I was like, maybe I could just like squeeze something. I really can't. Um, oh man. All right. Well, I'm going to do friction pay. Just like do the whole thing over. I don't want to though. Let's see. I'm going to go ahead and I'm going to get rid of this. We already know that the acceleration is 4.22 meters per second, so I'm going to erase this part and pretend that it doesn't exist right now. Here we go. If we add friction to this, there will be a third force acting on it. So instead of there just being a normal force going up in the direction perpendicular to the ramp, it will be going backwards. So I'm going to make my frictional force go back this direction with an arrow pointing backwards. Okay. And if I say that that's an arrow, oh, that doesn't matter right now. If the coefficient of friction is 0.4, then what we're going to have to do is we're going to have to calculate the force of friction using mu times the normal force. Okay, the normal force is 0.4. The normal force is what? Yeah, we've already calculated it using mg cosine theta to be 45.3 newtons. So if we multiply those two numbers together, that will give us the frictional force. 18.12? 18.12. Okay, so if we put in this force of friction, this is going to slow down the object a lot because now we have three forces. We have the normal force, we have the applied force, and we also have this force of friction, which is equal to 18.12. Okay, these two forces, the 21.1 and the 18.12, both of these are in the line of action. So since they're in the line of action, which I'm going to write LOA for line of action, since both of these are in the line of action, one of them is going down and the other one of them is going up, they're going to subtract away from each other. So the net force is literally both of these forces subtracted away because one of them is going to be pulling down the ramp and the other one's going to be pulling it up the ramp or trying to pull it up the ramp. Okay, but the net force is going to be negative in large. That does happen. Sometimes your friction is larger and sometimes the friction is what causes you to move. Okay, like you can move by friction. Like literally, you can move by friction. Like, well, yeah, an escalator is an excellent example. Or like if I take this cone and I drag the desk, I'm not touching the cone, but the cone is moving. Friction is actually what's causing it to move, right? So like an escalator is another example. Like the motor is not touching you, but you're moving up the escalator. You're moving up the escalator because of friction. You are walking from one class to another because of friction. You actually use friction to your advantage. Oh my. A world without friction would be pretty weird, to be honest. It would be, yeah, you wouldn't be able to move. Like nothing would happen. you would move around by like pushing yourself off of walls next to each other. But then if you wanted to get like super deep brain, you would be like, oh yeah, well technically you're never touching anything. Yeah, exactly. So like, why would everything hold themselves together if there's no friction? I mean, so like that's if you start thinking about like true, if you think about true frictionlessness, it doesn't make a lot of sense. Like friction to us is a normal thing, so much so that we take it for granted. So it's weird, but there's an incline problem. You want to try another one? Go ahead. Um, how would that affect the time? The acceleration would be lowered, and since the acceleration is lowered, it would cover the same distance in a smaller acceleration, so that would make it have a greater time. We totally have a new acceleration. We would have to recalculate the acceleration, and then we would have to recalculate the time based on the acceleration. Okay? And we can do that, but y'all asked for friction, so I gave it to you. There it is. Yeah, it's if you know the expression for how friction works, it's not too terribly bad. Okay. Now, friction also depends on the normal force. I've got like about 5-ish minutes, so I'm going to try to squeeze in this information. Um, the friction depends on the normal force, so you can increase friction and you can also decrease friction. Like, for example, if you have an object and you stand on the object, okay? If you stand on the object, you have two forces acting on it, so there is a force going down of mg, and then there is a force going down of the person as well. Because of that, the normal force has to work twice as hard in order to not push through the floor. So you increase the normal force, and therefore you also increase the amount of friction on the object. Okay? Like, here's an example. This is a piece of wood. This piece of wood has a particular piece of friction to it, right? So if I take this piece of wood, there we go, and I kick it, it's pretty easy to move, right? Okay. Now, stand on the wood. Is it easier or harder to move? Why? Did I change the coefficient of friction? No. I did not change, like remember the coefficient of friction is the number of grooves in between, right? I did not change the coefficient of friction, but I changed the normal force. So since there's more force pulling down on the object, there is a greater normal force pulling up, and friction is calculated by the coefficient times the normal force. So if you increase the normal force, then you're able to increase the force of friction. So that makes it much, much, much harder to move because these things are literally squished together into each other. Um, this vise, you can create a large amount of friction on things by just increasing the normal force. So if you take an object and you put it in there and you tighten it real good, okay, this thing ain't coming out. It's literally, oops, just kidding. Obviously not tight enough. Okay, but it's a lot harder to move out than actually just having it in there to start with. So yeah, try not to scratch anything. But you increase the amount of friction. So if you try to don't break anything, including your own fingers. There you go. Yeah, there you go. Okay, you're good now? No, it's literally like a part of it now. So like every time you try to move this, you're just moving the vise along with it now. That's because of the amount of friction. Okay. I don't have this anymore, but I may be able to find it downstairs. But there's the phone book trick. If you take a phone book and you put two of them together and you lay them out page by page, you can't pull them apart. That's because the amount of friction adds every single time you lay a page on each other. So by themselves, it wasn't a lot of friction, but when you put them all together, it makes it like 1,000 times greater. So it's like crazy to pull apart. I think there's like a MythBusters episode on that one, and it works. It works really good actually. So we'll keep trying to tackle friction tomorrow. Y'all have like 2 homework assignments that are up, and I'm kind of don't want to give y'all any more. So we'll keep working on those while we got them. So there we go.